Okay, yeah.
Very well. It's a pleasure now to continue our special session with a talk from Henri Darmon and elliptic curves, modular forms of weight one, and regulators of regulators.
So I want to thank you for organizing this session and inviting me to speak in it. So indeed, I changed a little bit the title of my presentation and the theme of the talk. And the main reason is that I've actually given a number of lectures on the topic I had previously announced, and so have my two collaborators, Jan Vonk and Alice Pozzi. And we realized that there are now a lot of videos out there online. And so I didn't really feel like repeating again this lecture, which I've given in a number of other occasions. So I thought I'd do something a little bit different. And what I decided to do in the end was to revisit some older work, which was in collaboration with Alan Lauder and Victor Roger. And the reason for that is that there were a number of questions that arose in this project. We haven't looked at this very recently, but there are still a number of questions that are open, and so I wanted to kind of bring them out and sort of have it somehow in recorded form. So I thought that the MCA would be a good opportunity to do that. So I'm going to talk about somehow connections with these so-called p-adic iterated integrals attached to a triple of modular forms and how they relate to the arithmetic of elliptic curves over certain extensions cut out by Artin representations. So I'm going to now present first the setting of this study. So we're going to associate certain numerical invariants to a triple of new forms, and the weights are going to be 2, 1, 1. One reason for focusing on these weights is that they're particularly concrete and appealing. So you could think, for example, a situation where F is associated to an elliptic curve over the rationals, and G and H, being classical modular forms of weight 1, are attached to certain two-dimensional odd Artin representations. And we can also then consider the four-dimensional Artin representation, which is the tensor product of these VG and VH. And that's still a representation with finite image, so it cuts out some finite extension of the rationals. And I'll denote by phi sub G the character of the Hecke algebra, the homomorphism which sends TL to the Lth Fourier coefficient of G. And I'll denote by I sub G the kernel of that homomorphism, which is an ideal in the Hecke algebra acting on modular forms of weight 1 and the level of G. Now, to this data, I have associated certain nice subspaces of the space of modular forms. So I can look at the G isotypic part of the space of modular forms of weight 1 and level n, character chi for some suitable Dirichlet character. So that's the subset of S1 where the Hecke algebra acts via the system of Hecke eigenvalues of G. And then that is also happens to be equal when G is a classical modular form of weight 1 to the IG isotypic part of in the much larger space of p-adic modular forms of weight 1, level n, and character chi. So here, the superscript of p here denotes a space of p-adic modular forms. Okay. But in the space of p-adic modular forms, which is infinite dimensional, the study, I mean, we know that the Hecke operators act semi-simply on the space of classical modular forms because they're self-adjoint relative to certain inner products, or at least normal operators. But on the space of p-adic modular forms, the semi-simplicity need not hold in general. And so one can look also at this so-called generalized eigenspace in the space of p-adic modular forms, which is simply the union of all the subspaces which are killed by the power of this ideal IG. Okay, so that they might not be annihilated by TL minus AL of G, but by some power of TL minus AL of G for all primes L. And so to this triple G, F, and H, we're going to associate what we call an iterated integral by doing the following thing. So we take this modular form H, which is of weight 1, and then we take the FP, which is this modular form F of weight 2, but we strip it of its Fourier coefficients at the primes, at the integers n, which are divisible by P. We look only at the prime to p Fourier coefficients. And we then take the inverse of that, which is the Q series. So if f was sum of a n q to the n, is the inverse of fp is sum of a n over n q to the n. And since n is always prime to p, this a n over n is at least a p-adic integer. And the resulting modular form is actually a p-adic modular form of weight 0, because this d is the so-called Atkins-Serre operator. It has the effect of raising the weight by 2, but if I take the inverse of d, which is only well-defined on p-adic modular forms, it lowers the weight by 2. So here we have a p-adic modular form of weight 0, which we multiply by a classical modular form of weight 1. What we are left with then is a p-adic modular form of weight 1. And what we do then with this modular form is we project it onto the generalized eigenspace attached to this other modular form G. Okay, so this expression is what we call an iterated integral. And it naturally lives in the space of p-adic modular forms of level n and character chi. Now, we say that the eigenform G, so a lot of the action, a lot of the subtlety about this expression is in the behavior of the p-adic modular form G and this so-called generalized eigenspace. So of course, this thing is easier to analyze if the generalized eigenspace is equal to the actual eigenspace. So we say that this eigenform G of weight 1 satisfies the Belaïch-Dimitrov condition at P if it satisfies the following equivalent conditions. At first, that the Coleman-Maser eigencurve, or the eigencurve associated with G, is smooth and étal at the classical point attached to this eigenform G. And it's étal over weight space. And the second condition is that the natural inclusion between the, so here I have a little typo in the slides. I really meant to take G here. The G eigenspace for S in S1 is equal to the G eigenspace in the p-adic thing, the generalized eigenspace. If the naturalized inclusion is an isomorphism. And these two conditions, it turns out, are completely equivalent. And so in this so-called Belaïch-Dimitrov setting, we can analyze this p-adic iterated integral and formulate the following conjecture, which says that this projection then of d inverse fp times h is a certain multiple of G, this classical form which generates this eigenspace. And the scale that comes up is something we understand completely, at least conjecturally. So this Rp of EFGH is a certain p-adic elliptic regulator attached to the pair of the elliptic curve and this four-dimensional Artin representation. So I won't write down precisely what this regulator is, but I'll tell you what it is roughly in words. It's going to be a 2x2, the determinant of a 2x2 matrix whose entries are p-adic logarithms of points on the elliptic curve, which are defined over the field cut out by this four-dimensional Artin representation. And one can be more precise about what points exactly. And so anyway, it's a 2x2 determinant. So it's a linear combination of pairwise products of logarithms of global points on the elliptic curve. And this UG, which appears in the denominator, is a certain Stark unit, which belongs to the field cut out by the adjoint of this representation VG, of the Artin representation. So the denominator is a little bit more simple arithmetically than the numerator. But anyway, this is the precise conjecture. And this conjecture has been checked numerically in a large variety of instances. With Victor and Alan, we wrote a paper some years ago where we gave a lot of numerical evidence for this conjecture. But what was interested now, and which is a little bit more speculative, is how one can try to relax these Belaïch-Dimitrov conditions. So the reason why they're called Belaïch-Dimitrov conditions to begin with is that Belaïch and Dimitrov wrote a very nice paper where they completely analyzed theoretically when the weight 1 modular form might fail to satisfy the BD condition. And this is true if one of these two conditions is satisfied. First, if G is a theta series attached to a character of a real quadratic field in which the prime P splits. So if G is a so-called RM theta series of a real quadratic field, and the prime P happens to be split in that real quadratic field, then we do not have this equality between eigenspace and generalized eigenspace. And the second scenario is the one where G is irregular at P. So G could be a completely general weight one modular form, but if the so-called Hecke polynomial attached to G has a double root for this Hecke polynomial at P, then again we have a sort of a richer generalized eigenspace. And the question then arises naturally then is what can we say about the iterated integrals in these two scenarios, where the iterated integral is something more complicated. It's not just some multiple of a fixed classical modular form. And indeed, in a numerical study, we were initially quite surprised to see that this quantity then, this projection onto the generalized eigenspace of the inverse Fp times H, is usually not a classical modular form. So one really has to contend with the non-classical components of this expression. And so the first problem then is to better understand this generalized eigenspace. So if you want to make a coherent conjecture, we should at least be able to say what the generalized eigenspace looks like, since that's the ambient space in which this iterated integral somehow lives. So we want to understand the space. We'll say something like, what is its dimension? Can one write down the Fourier coefficients of certain distinguished elements? So can we give a canonical basis, so to speak, of this generalized eigenspace in the space of weight one modular forms? And then once we have a nice basis, we can then ask if it's possible to predict what the Fourier expansion of this thing is in terms of that, or the coordinates of this expression in that nice basis. So I'm going to try to do that now. First, focusing on the case where G is irregular, but does not satisfy BD. So by this theorem of Belay-Dimitrov that I wrote down 2 slides ago, in that case, if the two Frobenius eigenvalues at P are distinct, then the only way that the Belay-Dimitrov condition can fail to be satisfied is if G is a theta series attached to a character of a real quadratic field, which is already kind of enticing, because then the field which is cut out by the Artin representation is an abelian extension of a real quadratic field. And so, of course, because the Artin representation wants to be odd, this character has to be of mixed signature. And we have to have, because of Belay-Dimitrov, that the prime P splits in the real quadratic field F. Now, what we can do is replace this theta function, this Hecke theta series attached to this character, by one of its P stabilizations. So this is just a modular form which has a P in its level and which is an eigenvector for the UP operator. And to choose this eigenvector alpha, it's one of the values of the character psi G at the primes above P. And there are 2 distinct such. I just choose one. Okay. What Belay-Dimitrov proved in this case is that even if there is this phenomenon that the eigenspace is, or the generalized eigenspace is larger, it's not so bad. The Coleman-Maser eigencurve is still smooth at the classical weight one point, which is associated to our theta series, but it's not étal. And it's the failure of étalness, which implies this extra non-classical or some extra non-classical p-adic modular forms of weight one belonging to that generalized eigenspace. And so okay, I won't say much about the proof. The proof of this result is purely Galois theoretic. Maybe that's the only thing I really want to emphasize. Namely, it arises because the tangent space and relative tangent space of this Coleman-Maser eigencurve above weight one are both one-dimensional, but then, so to analyze this tangent space, one has to consider the adjoint of the representation attached to this theta series. And that turns out to break up into 3 pieces. And these 3 irreducible constituents, the trivial representation, the Dirichlet character associated to this real quadratic field, which here I'm calling K, and the induced representation of psi, they each occur with certain multiplicities, 0, 1, and 0 in the units of the extension. Anyway, so if one analyzes this setup, one finds that one gets formulas for these generalized for these both the tangent space and the relative tangent space, and they both turn out to be one-dimensional, and that implies smoothness. Okay, I'm having trouble. Oh yeah, for some reason advancing. Okay, yeah. Okay, so I don't want to say too much about that. Let's just take that as a black box, so to speak. That this we have this thing. So in this setting, then we know that this generalized eigenspace, which we have here, is strictly larger than the classical subspace, and we say that a modular form which is not classical is a generalized eigenform attached to theta psi g. And the general yoga, okay, so then we can normalize it, because this generalized eigenform is only defined up to addition of any multiple of the actual eigenform, right, which is killed by a single power of Ig. And we can normalize this generalized eigenform in such a way by requiring that its first Fourier coefficient should be 0. So not like the usual normalized eigenforms where the first Fourier coefficient is 1. We say that it's normalized if its Fourier coefficient is 0, and that kind of pins it down up to a scalar, up to a multiplicative scalar. And the structure of this generalized eigenspace then is determined by a nice conjecture of Belaïch Dimitrov and Bettina, Adel Bettina, and Cho and Vatsal. So they actually conjectured that the generalized eigenspace would be as small as it possibly can be, subject to the restriction that we know that the eigencurve is smooth, but not étale. And so in some sense, that conjecture says that the ramification degree of the eigencurve is as small as it can possibly be, namely 2. And so that implies that there's only one extra non-classical eigenform. And if this conjecture is true, then that space, that generalized eigenspace, is spanned by the classical new form theta psi g and some extra thing, which I'm going to call theta psi g prime, which is unique up to scaling. And so we then want to understand is this theta psi g prime. What does it look like, and so on. So, for example, what is its Fourier coefficient expansion? And so it turns out that one has a nice answer to that. One can express the Fourier coefficients of this theta psi g prime in terms of p-adic algorithms of certain units or L units in the extension cut out by the adjoint. Okay, and in fact, these units had already been studied before. They're the units that arise in the p-adic variant of the Stark conjecture. Really, you should maybe say the L-adic variant, rather, of the Stark conjecture. So there's a nice theorem of, there's a theorem that Dasgupta, Pollack, Ventullo, and I proved some time ago, that if we take a psi to be a character, I mean, to be that mixed signature character, then there's a unit UP of psi, whose logarithm is actually the derivative of this certain p-adic L function associated to psi. Okay, so good. So we have this now. The case in the case of this, if we take this character psi g, which is a mixed signature, we can look at its the ratio of psi g and psi g prime, and we get a totally odd character, a ring class character of the real quadratic field. And this character is totally odd, and every prime which is inert in the real quadratic field actually splits completely in this abelian extension of F. And so there's therefore a non-trivial L unit in the spirit of the Gross-Stark conjecture. And one can even define a canonical normalization of this so-called Gross-Stark L unit, essentially by requiring that the valuation at L should be exactly 1. Okay, so in terms of those invariants, we can say something about the Fourier coefficients of this extra non-classical eigenform theta psi g prime. Namely, there's a unique thing, a unique normalized generalized eigenform, which can be scaled in such a way that the L Fourier coefficient is the logarithm of this Gross-Stark unit at L, if L is inert in F, and is equal to 0 if L is split in F. And therefore, and more generally, here's the general formula for the nth Fourier coefficient of this generalized eigenform. So you can see that it's very much a non-classical object because the Fourier coefficients involves logarithms of different algebraic numbers. So the transcendence degree of the field generated by the Fourier coefficients is infinite in particular. Okay, so here's a numerical example of this. So if we take chi to be the quartic Dirichlet character of conductor 5 times 29, and we look at the modular forms of weight 1 and level 5 times 29, it turns out that this space is one-dimensional. It's spanned by a single theta series, single Rm theta series, associated to a quartic character of the real quadratic field q square root 29. And this quartic character is ramified at one of the primes above 5. Okay, so this is exactly the scenario where you get these things. And this theta psi g is an interesting object because it's not a CM theta series. So it's induced from a character of a real quadratic field, but not from a character of an imaginary quadratic field. And in fact, the level 145 is the smallest level where this happens. Okay, so we can now consider a prime P, which is split in this real quadratic field, okay? And where theta psi is regular. It turns out that the smallest prime with that property is the prime 13. And so then the BD conditions fails in an interesting way, and we can compute this, we can look at this quartic character of conductor 5, which is a cyclic quartic extension of the real quadratic field. And well, we can compute then the Fourier coefficients of the associated generalized eigenform. And it turns out that the ELF coefficient is the 13-adic logarithm for this prime P. So now we work at the prime P equals 13, and I view this as a 13-adic overconvergent modular form. And I get that the ELF Fourier coefficient is this 13-adic log, at least experimentally, of this certain L unit. And here it's written down precisely as a combination of a certain with coefficients in the field generated by the Fourier coefficients of these of certain L units in the Hilbert class, or the Ray class field, ring class field of conductor 5 of q square root 29. And for example, the 2 unit is given by this rather complicated formula. And here's a little table. I don't know if you can see it very clearly on Zoom, but for the first few primes, we computed the L unit UL, whose 13-adic logarithm gives you the Fourier coefficient of this theta psi g prime, at least to 20 digits of accuracy. But here we can actually prove everything. It's not just a conjecture with experimental data, but it really is actually a theorem. Okay. Now, what we conjectured with Alan and Victor some time ago is that if we take this iterated integral, this non-classical modular form, and we project it onto this generalized eigenspace, we will get a multiple of this theta psi g prime by a certain numerical quantity, this regulator. And this RPE VGH, it's exactly the same p-adic regulator that arose in the original conjectures. So it's the same 2x2 determinant formed from E and VGH. And but what's more mysterious now is this omega g. So there's a certain p-adic invariant which ought to depend only on G and not on F and H. And it's a kind of a p-adic period associated to G. Now, what we were never able to, so in the original case of our conjectures, this p-adic period was just a logarithm of a certain Stark unit in the field cut out by the adjoint. In this setting, that Stark unit turns out to be trivial. And we were never able to actually give even a conjectural recipe for what this omega g is. So that's one of the first mysteries, is that, I mean, we were able to check this conjecture indirectly by taking any pair, by varying F and H essentially, and looking at the ratios. And then we found that the ratios of these two quantities gave us the ratio of the regulators. But we were never able to actually pin down this mysterious omega g. And that's a very tantalizing invariant, which is associated to one of these theta series attached to a real quadratic field, where P is split in the real quadratic field. And we'd very much like to have some theoretical insights into the nature of this period. Okay, so the special case is the one where H is where this H is also associated to the same real quadratic field F as is the G. And in that case, the Artin representation VG tensor VH breaks up into essentially a billion characters of F. Okay, so then we have this tensor product here. It becomes a sum of two induced representations of two characters of F. And then this p-adic regulator that appears in the denominator of this conjecture turns out to be a simple product of two logs of points on the elliptic curve, which are in the field cut out by these characters psi1 and psi2. And then, so these live in the ring class fields of the real quadratic field. So they're very interesting points. They're kind of analogous to Heegner points on the elliptic curve, but now they're defined over a ring class field of a real quadratic field. So they're beyond the scope of the theory of complex multiplication. And we'd be very much interested in understanding these points and how they relate to the arithmetic of the elliptic curve over a billion extensions of real quadratic fields and so-called Stark Heegner points that were introduced some time ago and studied also by Victor and me and others. Okay, by the way, how much time do I have? I haven't been keeping track of the.
It's been half an hour just now.
Okay, but I have
so 10 more minutes.
10 more minutes. Okay, that's perfect. Yeah, okay. So that's what I thought. I have 40 minutes, right? So I should end at 12:55. I mean, with all these different time zones, it's a bit hard to keep track. Okay, so at 12:55, perfect.
We started a few minutes after that, so.
Oh, it's fine. I'll be done. So I wanted to now talk about the other setting, the case where the Coleman-Mazer eigencurve is not smooth at the weight 1 point, which arises precisely when the modular form of weight 1, G, is irregular. So if G is an irregular weight 1 form, then the kernel of IG squared is, yeah, I mean, so the generalized eigenspace actually is spanned by these, this G and G of Q to the P. Yeah, here there's a typo actually. I don't know what, I mean, I really meant this S1 of N chi IG, the eigenspace. The eigenspace is, no, sorry, this is the classical subspace. It's perfectly fine. I mean, what I meant to say here is that IG doesn't act, I mean, the Hecke algebra doesn't act semi-simply even on the space of classical forms. And that's because of this lack of regularity. So the classical space is a two-dimensional, spanned by G of Q and G of Q to the P. But the generalized eigenspace is larger, right? So it's it's made up of this direct sum of the classical space and the normalized subspace of the p-adic modular forms. And we say that an overconvergent generalized eigenform is normalized if its first Fourier coefficient and its pth Fourier coefficient are both equal to 0. And when I look at this normalized subspace, it's a sort of a natural direct summand in the space of all overconvergent modular forms. So it breaks out the space of classical forms. And so what we want to do then is give a description. And now the conjecture that we formulated, and there's now some evidence for this conjecture, is that this space, this generalized eigenspace, is actually four-dimensional. In other words, the space of normalized non-classical modular forms is two-dimensional. And one can actually describe in a very concrete way this normalized subspace of the p-adic modular forms, namely in terms of the adjoint representation of VG. So to give this description, I need to introduce a certain inner product on the space of, well, 2 by 2 matrix, I mean, the adjoint with WG. So if I take these, I think of these as endomorphisms of VG, then there's a natural inner product, which is just given by taking the trace of AB. And then there's also a Lie bracket. If I think of endomorphisms of VG, I can take this usual Lie bracket. And then there's also a determinant function. Given a triple of elements of trace 0, I can take the inner product of A with the Lie bracket of B and C, and this has all kinds of nice symmetry properties. It behaves like a determinant. It's a symmetric alternating trilinear form on the adjoint, on the adjoint. So if I let H be the field cut out by this three-dimensional adjoint representation, and G the Galois group of this field, then the Dirichlet unit theorem tells me that if I take the units of this field and I tensor with this WG, this three-dimensional representation. I take the G invariance, I get something of dimension 1. That arises simply because of the fact that complex conjugation has a single eigenvector with eigenvalue 1 on this three-dimensional adjoint representation. And but on the other hand, if I look at the L units of this field, if I take OH1 over L star, then the dimension is either 2 or 4. And it's 2 if G is regular at L, and 4 if G is irregular at L. So you always get an extra L unit when you pass from the units to the L units, but you get a single one if G is regular, and you get more if G is irregular. And so if I can now fix a generator for this group of units, and for every prime L, for every regular prime L, I can look at this UG of L, which will be the p-adic log of a certain element in OH 1 over L star tensor WG. And this is well defined, this UG of L is well defined up to translation by multiples of the UG, the canonical Stark unit. Okay, so you have the L units, and then you inside there you have the units. Okay, and so the conjecture then is, well, we can give a description of this normalized space. And if we believe the conjecture that it's two-dimensional, then we state that there's an isomorphism between WG tensored with CP modulo the line which is spanned by this UG, by this Stark unit. And that lands in the space of p-adic over convergent modular forms in its normalized space. And what determines this isomorphism is what it does to Fourier expansions. Namely, if I look at the image of a vector W in the space of normalized eigenforms, then the L Fourier coefficient of this modular form is the determinant of W, this vector here, the Stark unit UG, and the Stark unit UG of L. If G is regular at L, and if G is irregular at L, so if L is an irregular prime for G, then the L Fourier coefficient is just 0. So this gives you a complete parametrization of this generalized, normalized subspace of the non-classical generalized eigenforms attached to G, which everything is depending only on this Stark unit of G and the L units. Okay, so now we can define a nice elliptic regulator attached to E and this four-dimensional Artin representation. And it's going to depend on choosing a UP eigenvalue for G. But this is actually ill-defined when G is irregular, okay? Because then there's this eigenvalue occurs with multiplicity 2. But what we can do is we can define the regulator to be 0 if if the G invariant subspace of the Mordell-Weil group tensor VGH is not equal to 2. And otherwise, we can consider the following sequence of maps. We can take the second wedge power of the G invariance of this E of GH and VGH, so that we map that naturally to the symmetric square tensored the second wedge of VGH. And then there's a nice little piece of representation theory. So this VGH is a four-dimensional Artin representation, so its wedge square is a 6-dimensional Artin representation. But that 6-dimensional representation actually breaks up as a direct sum of the adjoint of G and the adjoint of H. And so we again can project onto the part which depends on G, so the adjoint of G. And so we land in this thing. And then now we have sim squared of the Mordell-Weil group, tensor of WG. We can, on this symmetric square of the Mordell-Weil group, there's naturally a linear form, which is the logarithm tensor squared. And that lands us in WG tensor CP. And we then define the elliptic regulator to be the image of P wedge Q under the sequence of maps, okay, where P and Q are generators for the Mordell-Weil for this thing, E of G, HGH, tensor VGH, G invariance. Okay, so when you do that, you land in this thing. And then the conjecture that we made is that for all irregular G, the G isotypic part of D inverse FP tensor of D inverse of FP times H is the image under phi of this p-adic regulator. Okay, so that gives us some overconvergent form divided by a suitable period, which depends only on G. And so, okay, so that is a conjecture that one can actually check numerically because everything here is completely explicit. And one can vary the G and the F and the H in order to eliminate the dependence on this mysterious period omega G. Okay, so the conjecture implies that for all primes that are regular for VG, the L Fourier coefficient of this modular form, of this overconvergent modular form, is up to elements of L star, the field generated by the Fourier coefficients of G, is equal to this determinant of this 3×3 matrix, whose entries are mostly p-adic logarithms of units and L units in the field cut out by the adjoint of G. But the first row of the matrix is a little bit more complicated. It's an elliptic regulator, which is formed by 2×2 determinants of logarithms of points in the Mordell-Weil group of the elliptic curve over the field cut out by the four-dimensional representation VG tensor VH. So this is what we call regulator of regulators because it's a matrix whose entries are themselves regulators, and we take the determinant of that matrix. Okay, good. So I'm now almost done. Okay, I mean, now I can, for some reason, my screen is not advancing anymore. Okay, so, okay, where these points are in the Mordell-Weil group, etc. Okay, so I just want to conclude by saying that there has been a lot of experimental evidence for this conjecture. By the main workhorse in gathering numerical evidence for this is the wonderful algorithm of Alan Lauder, which allows one to very efficiently compute ordinary projections on spaces of overconvergent modular forms of weight 1, even when the dimension of the space of overconvergent forms is quite large. Okay, but there are a lot of questions that remain. Well, one would like to have some better understanding theoretically of this overconvergent generalized eigenspace, and one would like to understand the mysterious periods omega G in the case where G is either a theta series of a real quadratic field where P is split, or where G is an irregular modular form, and that's still quite mysterious. We don't have much even conjectural insights into those questions. So I'll stop here and thank you for your attention.
Are there any questions? If not, we can thank the speaker again.